Alright, so let us start this chapter on reflection and refraction. It is a very important topic. The questions on this are very common. So before we start this chapter, I would highly recommend that if you have not gone through the video number 3, which is on wave and wavefront, please go through it because we'll be understanding reflection and refraction in this video, both in terms of waves and wavefronts. So please go through video number 3 and come back to this video to understand this chapter nicely. So let us start. So here on the screen you are given two scenarios. Scenario 1, reflection. Scenario 2, refraction. So what is happening? We are going to understand both reflection and refraction now, starting from now. So reflection happens from a smooth surface, right? So our light ray falls on the smooth surface and it bounces back. It is a hard but a smooth polished surface. It can be a mirror or any other smooth surface. Refraction happens. When does the refraction happen? Refraction happens when a light ray comes from one medium and enters another transparent medium, right? Say that a light ray is coming from one medium and it is entering another transparent medium. It bends while doing so. It can bend this way as is showing as is shown here, or it can bend this way. It can bend any which way. It depends on the properties of the substance. It depends on the property of the transparent substance in which the wave is traveling to. So we are going to start to understand both these things. A normal, it is a straight line at right angle to the mirror or the boundary. So where is the mirror here? This is your mirror. So if you can draw a right angle to the mirror, or if you can draw a right angle to the boundary. Where is the boundary? Here, if you see this line is your boundary. Why? Because it is a boundary between two different mediums. Before the boundary you have one other medium, maybe it's air, and under the boundary you have another medium, maybe glass or water. Maybe this is your glass, or it can be your water, and this is your air. So this is your boundary and this is your mirror. So a straight line at right angle. So let us draw the normals here. Here, that's how you draw the normals. These are your straight lines at right angle to the mirror or the boundary. Next thing, incident angle. It is the angle between the incident ray and the normal. So before we draw the incident angle, let us draw the incident ray. So a ray is falling. It is coming and falling at the foot of the normal, right? This is your incident ray. So in both the pictures, if you see, this is your incident ray. Incident ray. Here it is your incident ray. So you have drawn the incident ray. What is the angle of incidence? It is the angle between the incident ray and the normal. So can you identify where is the angle of incidence? Right here. Angle between the incident ray and the normal. This is your normal. Let me write it N. Angle between the incident ray and the normal is your incident ray. So what happens next? Reflection is happening. Reflection, let us focus on the reflection part of the screen. You have created a reflected ray. Let me write the name of the ray. It is your reflected ray. And how do you draw the reflected ray? You have to draw the reflected ray taking care that the angle of incidence is equal to the angle of reflection. The angle of reflection, where is the angle of reflection? Reflection If you see this term, it is the angle between the incident ray and the normal. So whenever the reflection happens, you have to take care that the angle of incidence should be equal to the angle of reflection. This term here is reflection. If you focus on refraction, you have found out the refracted ray. So let us write down the name of the ray. It is your refracted ray. Is the refracted ray moving as it was moving in the case of the mirror? No, it is passing through the transparent medium. Both the mediums, say that the incident ray was in the air, it will move through the other transparent medium, which is in gray here, which can be water or glass or any other substance. It can pass because it is transparent. But as it is passing, it is bending. If you see, it is bending, right? We have identified the incident ray, we have identified the refracted ray. We do not call it reflected but refracted ray. Let us identify the angle of refraction. The angle of refraction, which is also denoted by R, is the angle between the refracted ray and the normal. So pause here for a while, and can you mark the angle of refraction on the screen? This is your angle of refraction. Alright, so now today in this video, just now we have understood what is reflection, what is refraction, how reflection happens, and when refraction happens, what are the angle of incidences, what is angle of refraction. They all have to be drawn. The first things first that you have to do is start with drawing the normal first, because the angle of incidence and the angle of refraction, they both are measured from the normal. So normal, if you see, it is very important. So first things first, draw the normal. Angle of incidence, angle of refraction, everything is measured from the normal. So let us move on to understand how the same process, the same phenomena is happening when you're given the wave fronts. You're given the wave fronts, but you're not given the waves, as you see in the question here. So this is a case of reflection. You are given a set of wavefronts. If you see, you are given 3 wavefronts, 1, 2, and 3, and you have to find the reflected wavefronts. So how do you do this? Do this as a step-by-step process. What do? You draw the incident wave perpendicular to the incident wavefront. So you are given the wavefronts. We know that the incident wave would be perpendicular to the wavefront. So if you see yellow line, it is the wave. Yellow line is the wave. Let me write it down here as well. So the yellow line that you see here, that's your wave. And the blue lines that you see here, these are your wave fronts. So the incident wave will be perpendicular to the incident wave fronts. Now you have identified the incident wave. You have found the incident wave. Reflected wave, you know how to find out. Simple and easy. We have just done it. Reflected wave, you have to draw, taking care that I is equal to R. So where is I? This is I. You have identified I. Draw the reflected wave. You can pause the video here for a bit. Come back and play the video. So here is your reflected wave. You have to take care that I is equal to, R. I should be equal to R. Alright, so next thing now, the last thing that you have to do is to draw the reflected wave fronts, because that's what the question would be about. You are given the set of incident wave fronts. Draw the reflected wave fronts. How do you draw the reflected wave fronts? You have found the reflected wave. Reflected wave fronts would be lines that will be perpendicular to the reflected wave. As simple as that you have done this question. You started with a set of incident wave fronts. You identified the incident wave and the reflected wave. Now the reflected wave fronts will be perpendicular to the reflected wave. We know that wave and wavefronts are perpendicular, right? So this is what you should be doing in your exams. Now, one important thing to note. Note for the students, very careful, pay attention. The spacing between the incident wavefronts, if you see the spacing here, should be equal to the spacing between the reflected wavefronts. Why? Because reflection does not change your wavelength. The spacing here, the perpendicular spacing should remain the same everywhere. The perpendicular spacing everywhere, be it at the incident side or be it at the reflected side, it should always remain the same. Why? Because this means that the wavelength does not change when the waves are reflected. Alright, makes sense? So this was about the reflection of wavefronts. Easy, not so difficult if you follow the steps. One by one, it will all make sense. Please do understand the relationship between waves and wavefronts if you have not gone through it. Alright? So now we'll be learning about refraction. So this screen will focus on refraction. Refraction of what? Wavefronts. What kind of wavefronts? We'll focus on water waves. So we are focusing on water wave. That's the part of your IGCSE syllabus. So we'll stay focused. We'll be focusing on refraction of wavefronts of just water here, which is a part of your IGCSE. So some things very important for you to understand. Let us focus on the first part of the screen. Let us not focus on this side. Let us focus on the first part of the screen. What is happening here? If you see, water wavefronts are coming from a deep region of the water. Water is coming from a deeper region and it has entered our shallow region. Alright, so try to visualize water is coming from a region where the depth of the water is more and it is entering the second region, which is shallow, deep and shallow. When wavefronts, so I'm at point number 1, when wavefronts travel from deep to shallow, their speed reduces. Now this is something that you need to remember here. Deep to shallow, what is happening? Some straightforward relationships you'll get, so you'll never forget. So what is happening here? The depth is going down from the part 1 of the picture to the part 2 of the picture. What is happening to the depth? Depth is going down, which implies the speed goes down. So when the wavefronts travel from the deep to the shallow region, their speed will go down. They bend towards the barrier. So let us see what is happening. Angle also going down. So let us call the angle as alpha. Their angle is also going down. They are bending towards the barrier. So let us see how the angle is going down. Like this. The angle is going down. But they are again parallel. If you see, they are parallel lines. In the shallow region also, they are parallel lines. So what angle we are talking about? Say this was the angle with the barrier earlier. Let us call it alpha 1. This is the new angle, alpha 2. If you see, alpha 2 is less than alpha 1. The angle is going down. The angle with the barrier is also going down. So therefore, the last point, smaller wavelength. How a smaller wavelength? Let us understand in the picture. The wavelength is the distance between the wavefronts. So this was your wavelength earlier. Wavelength, if you remember, is the distance between the wavefronts, perpendicular distance. Please go through my video on wave and wavefronts to understand this point if it is not making sense to you now. If you go through that video, it will make perfect sense to you. How do you identify the wavefronts? How do you identify the wavelength when you are given the wavefronts? It is the perpendicular distance. You now know the new wavefronts at the shallow side. So what is the new wavelength on the shallow side? Perpendicular distance again. How much is it? Say it is lambda 2. You can clearly see that lambda 2 is less than lambda 1. So what is happening to the wavelength as well? The wavelength is also going down. Everything is going down. The depth is going down. Whenever you see that the depth goes down, you should understand that the speed is going down. As a result, the wavefronts will travel closer to the barrier. The angle goes down and the wavelength goes down. So let me rewrite this whole thing in a sequence. The depth is going down here. The depth of the water is going down. Therefore, the speed is going down. The angle with the barrier is going down. The wavelength is going down. This is what is happening in this scenario. Let us now focus on the second scenario, when the wavefronts travel from the shallow to the deeper region. So here in this picture, what is happening? The wavefront is moving from the shallow. The waves are coming from a shallow region of maybe a water body, a sea or a river, and it is entering a deeper region. So what can you say? Shallow to deep. Shallow to deep means the depth is increasing. What happens to the speed as a result? The speed increases. What happens to the angle as a result with the barrier? They bend away from the barrier. They bend away from the barrier. Let us draw the wavefronts when they are bending away from the barrier. So they'll be bending something like this. Let me draw it. They'll be bending something like this. Like this. These are your new wavefronts. They are bending away. How they are bending away? Let us find the angles. So this was your alpha 1. This is your alpha 2. So clearly if you see, alpha 2 is greater than alpha 1. They are bending away from the barrier. As a result, what happens? As a result, the wavelength is also going up. Let us compare the wavelength. Let us mark the wavelength. Where is the wavelength here? Perpendicular distance. This line that you're drawing, it has to be 90 degrees. This gives you the wavelength. This is your lambda 1. Here if you draw the perpendicular distance, it would be like this 90 degrees line. It has to be a 90 degrees line. If you see, the spacing between the wavefront has gone up. Spacing between the wavefronts, lambda 2 is greater than lambda, I'm sorry for this small mistake, lambda 2 is greater than lambda 1. So the new wavelength, which is lambda 2, is greater than the original old wavelength lambda 1. So very easy to memorize. When the wave is traveling from deep to shallow, I am summarizing. Deep to shallow, depth goes down, the speed goes down, the angle with the barrier goes down, and therefore automatically when you do the construction of the wavefront, because the angle is going down, when you construct the new wavefronts at a smaller angle, automatically visually you'll see that the spacing between the wavefront is going down. So what is happening? What can you infer? That the wavelength is going down. Similarly, when the waves travel from shallow to deep, the depth is going up, the speed goes up. Therefore, the angle with the barrier goes up. Now you draw the wavefronts with the greater angle with the barrier, and automatically you will see that the spacing between the wavefront is going up. Spacing between the wavefronts, compare the spacing here and here, it is going up. So what can you infer? That the wavelength is going up. Alright. This is a very common IGCSE type of questions asked almost every year. Fine. So if you still have any further doubts, please leave your questions in the comment box. I'll answer each and every one of them. So why this happened, what we have just learnt, right? Let us understand. Refraction can be explained as follows. Let us explain what we have just learned. The frequency of the waves remains unchanged in different mediums, no matter where the waves are. Whether the wave is in a deep region or the shallow region, it is in air, water, glass, or any medium, frequency of the wave is a factor which remains unchanged, right? And we know the wave equation. We know the wave equation, which is speed is equal to frequency times lambda. The speed of the waves change in different medium. Frequency never changes, it is the speed which changes. It is the speed which changes. So if you have to have this equation holding true all the time, whenever the speed changes in such a way that the speed is going up, the wavelength also has to go up. Whenever the speed increases, the wavelength increases. This is just we saw in the previous slide. Whenever the speed will increase, the wavelength will increase, because this particular term frequency here, it stays static. It never changes. Whenever the speed will go down, the wavelength will also go down, so that this equation, the wave equation, can hold true. This comes from, the explanation comes from the wave equation. So this is an important thing that you need to remember, that the frequency of the wave, of any kind of a wave, be it water wave, light wave, sound wave, it does not change from one medium to another medium. It is only the speed which changes. Whenever the speed will increase, the wavelength will increase, so that the wave equation holds true all the time. Whenever the speed goes down, the wavelength goes down, so that the wave equation holds true all the time. Alright, so this was the explanation about refraction. The next chapter will be on diffraction.